Today we're going to talk about one of the classic problems of calculus. It's called a solid of revolution. Let's get started. Imagine we have the graph y equals x to the 1/3. That's this red graph here. That's that function. Hopefully you recognize this as a cube root function. It's missing the other part down here, but that's because we're only going from 0 to 8. So that red line is the y equals x to the 1/3 from 0 to 8. Imagine that you've got that graph on a piece of paper, and you take that graph and you spin it around in a circle. So you rotate it around the x-axis. What you're doing is, if you imagine the space underneath it being spun around in a circle, you're making a solid of revolution. You're making a solid shape made up only of the area underneath that curve. What we want to do is find the volume of that solid shape. It's not quite a cone, it's not quite a cylinder, it's somewhere in between. But that solid shape is made up of a bunch of slices. Not exactly a technical term, but here is one of those slices. And if you can imagine, there's just everywhere you go, and at every x value, you have the y value of the curve. So that would be x to the 1/3. And if you imagine spinning it around in a circle, spinning it around the x-axis, what you're doing is you're making a circle whose radius is that y value. So now we can talk about the area of that circle using using area equals pi r squared. And then here's the magic. What you're going to do is imagine that that circle is no longer a flat piece of paper, but imagine it as having a little bit of thickness, sort of like a coin. So now what we've done is we've taken that flat circle, and by giving it a little bit of thickness, it has volume, because now it's a solid object. If you imagine it's sort of like a stack of American cheese slices, each one is very, very thin, but when you stack them on top of each other, it takes up a lot of space. And so what we can do is figure out the volume of the small little slice that we've made. And then if we just find the volume of every other small little slice that we made and make another one here and find the volume of that the same way, if we add up all of the volumes of all of those slices, we'll have the volume of the entire object. So that's our goal. And we're going to use the same dimensional analysis that we used last class talking about area. One dimension at a time. And I set the table for us to do that when I drew the slice that's over here. I said we started with the radius of the circle is the y value of that curve. The blue dotted line that I have here is the radius of the circle, and we got it by finding it's the height of the function y equals x to the 1/3. Oops, not x times 1/3, x to the 1/3. So that is, at any x value, the radius is x to the 1/3. And then our next step is to take the radius of that and make it into our two-dimensional circle. And we can find the area of that circle. And we mentioned earlier, the area of a circle is pi r squared. But since we know that the radius is x to the 1/3, we can call that pi times x to the 1/3 squared, which is x to the 2/3. And our next step is to go from a two-dimensional area to a three-dimensional volume, because we want it to take up space. And that's where the little thickness comes in. Adding this little bit of thickness here makes it a solid object. And so we need to figure out what the volume of our new solid object is. And I'll remind you a little bit of geometry. The volume of a cylinder, or a circular prism, just like the volume of any other prism, it's the area of the base times the height. That's the volume of a prism. Our tiny little slice here, our little disc, our coin that we've got here, is a prism. The area of the base is the area of the circle that we've got here, and the height is this tiny little thickness there. That's the height. Well, we've used a different name for that thickness before, which is what we did last class. That is our dx. That is our small little tiny incremental change in the x-axis. So if I want the volume of a slice, and just like we talked about the area of a strip last class, we called it dA. The volume of a slice we're going to call dV, that's important, is equal to the area times the thickness. Or in this case, the area was pi x to the 2/3 times the thickness. So this is the volume of our slice. If we want to find the volume of all the slices put together, if I want the volume of all of our slices put together, we're going to have to take the volume of a single slice and just add it up for every x value. Well, this is a product, the area of the base times the thickness, and we have a name for the sum of a whole lot of products put together. That's the integral. So the overall volume is going to be the integral from start to finish, I'll talk about that in just a second, of the area of our base times the thickness. And start to finish, since our dx's are going in this direction, they start when x is 0 and they end when x is 8. That is the biggest radius, because that's what they told us. So we'll go from 0 to 8. And then we can integrate that. This one we can do using the power rule. Using the fundamental theorem, the volume is equal to the antiderivative of pi x to the 2/3, which is pi times x to the 5/3 divided by 5/3, evaluated from 0 to 8. Please make sure that you include the evaluated from 0 to 8 when you change the definite integral into its antiderivative. You have to make sure you include the evaluated from 0 to 8. And so that would be 3/5 pi, let's put that on the outside, factor that out, times x to the 5/3 evaluated at 8 minus x to the 5/3 evaluated at 0. And 8 to the 5/3 is actually not that hard, because remember the thirds is the cube root. So the cube root of 8 is 2, and 2 to the 5th is 32. So we've got a numerator of 3 times 32 pi over 5, and that is our volume. Because it is volume, the unit of measure would be cubic units. They didn't tell us if it was inches or centimeters. But I want you to notice why it's cubic is because the radius was measured in, let's say, centimeters. I know we didn't say centimeters, but let's pretend we did. And then when we take that and we square it, that's centimeters squared. And then when we take the area and multiply that by dx, well, the x value is also measured in centimeters, so dx is in centimeters. And that's why we end up with centimeters cubed, because we keep multiplying by the centimeter units over and over again. So that is the volume of this solid.